Welcome back to Calculus 2. This is your Exam 2 review. We've spent a lot of time studying techniques of integration, and I've kind of tried to enumerate those as four. There are really only two methods: substitution and integration by parts. However, I like to enumerate those as follows. 1. Substitution. You use that if you see the derivative of something lying around or some impediment. 2. Trigonometric substitutions. You use those if you have either a sum or difference of squares under a radical, and you leverage the trigonometric identities, the Pythagorean identities, to try to reduce that to a single perfect square that allows you to get rid of the square root. 3rd, partial fractions, which is really an algebraic technique designed to take rational functions, and those are polynomials divided by polynomials, and separate those into simpler terms that are easier to integrate. And finally, integration by parts as a last resort. So for our first example, we have the integral of x divided by x squared plus 3 to the power of 99 dx. Clearly we see the derivative of something lying around. So we'll set u to be the thing that has its derivative lying around. In that case, du is 2x dx. We don't have the 2, so we'll divide that off. I'll encapsulate this. This allows us then to transform the integral into 1/2, this 1/2 from the du, 1/2 x, the x dx gets replaced by 1/2 du, and then what's left over is 1 over u to the power 99. You can't integrate this directly until you move the u across the division symbol and into the numerator. Then you may use the power rule for anti-differentiation. So we'll write this as the 1/2 times the integral of u to the negative 99. We'll use the power rule to write this as 1/2 times u to the negative 98 divided by that negative 98 plus c. And you're not done until you substitute in for u. To complete the problem, we replace u with what is equal to x squared plus 3. Let's see, we have negative 180 plus 16 is 196 plus c. And I suppose we should simplify this by getting rid of the negative exponent. On the exam, I won't make you do that. Yielding our final answer. For problem 2, we have the integral of the square root of 9 minus x squared dx. We clearly have the difference of squares under a radical. That's a clear indication that this is a trigonometric substitution problem. So, because it's in the form constant minus variable squared, it's the sign identity that we use. In general, 1 minus sine squared theta is cosine squared theta. So if you have constant minus variable squared, it's going to be a 1 minus sine squared. You'll use a sign for the substitution. The square will come from the square here. If you have a plus, you use the identity 1 plus tangent squared theta equals secant squared theta. And if you don't remember this identity, it's always easy to derive. Your typical Pythagorean identity is cosine squared plus sine squared equals 1. If you divide everything in sight by cosine squared, you get 1 plus tan squared theta is secant squared theta, confirming this. The third option, the third possibility, is if you have variable squared minus constant. In that case, move the 1 over and you'll get secant squared theta minus 1 is tangent squared theta. And you'll use this identity in that case if you have variable squared minus 1. In this particular problem, we clearly have this case. You take the square root of the variable part and set that equal to the square root of the constant, whatever that is, times the sine of the new variable theta. In this case, dx will be 3 cosine theta d theta, yielding our substitution. I will encapsulate that into a box so that we can keep it apart from our main computation. The integral is transformed. We'll have the square root of 9 minus 9 sine squared and dx gets replaced by 3 cosine theta d theta. Under the radical, we'll factor that as 9 times 1 minus sine squared theta. The 9 is still under the square root. When we take its square root, we'll get 3, combine it with this other 3. That'll give us 9 times the integral. We'll have 1 minus sine squared, which is cosine squared. Now we have a single perfect square under the radical, the cosine squared. The square root and the square will cancel each other out, leaving just a cosine, and then we have this other cosine, leaving us with the integral of cosine squared theta d theta. It's necessary now to use our half angle identity. Cosine squared theta is 1/2 1 plus cosine of 2 theta. We have then 9/2 times the integral of 1 plus cosine 2 theta d theta. So we have this 9/2. The integral of 1 will be theta. The integral of cosine, because of the 2 theta, we'll have a factor of 1/2. You always have to divide by whatever the coefficient of your variable is. The sine of 2 theta plus c. At this point, we have to back substitute, but we also need to use a double angle identity for sine. The sine of 2 theta is 2 sine theta cosine theta. So this gets replaced by 2 sine theta cosine theta. The 2 and the 1/2 will cancel. At this point, keep in mind, x divided by 3 is sine theta. We'll make a right triangle. Sine is opposite over hypotenuse, and so the remaining side, using the Pythagorean theorem, will be the square root of 9 minus x squared. That has to appear again, or else you screwed up. At this point, theta will be the inverse sine. Of x divided by 3. And to this we have to add sine theta cosine theta. Sine theta is x divided by 3. And cosine theta is the square root of 9 minus x squared divided by 3. For purposes of the exam, you can drop the answer right here. On problem 3, we're evaluating the square root, in this case, 9 plus x squared. Because of the plus, we'll have to use tangent, and the identity 1 plus tangent squared theta equals secant squared theta. So you'll take the square root of the variable, set it equal to the square root of the constant times tangent theta. So dx will be 3 secant squared theta d theta. We'll encapsulate that in a box. The integral becomes the integral of the square root of 9 plus 9 tangent squared theta times 3 secant squared theta d theta. The 9 can be factored out of the square root as a 3 and combined with the other 3 to become a 9. We'll have 1 plus tangent squared under the radical. According to the identity, that equals secant squared theta. The square root of secant squared theta is secant combined with the secant squared. We're integrating secant cubed theta d theta. How do we integrate the secant cubed theta d theta? And the answer is by parts. We'll split this off as a secant theta secant squared theta d theta. Integration by parts says there's a part you'd rather integrate and another part that you'd rather differentiate. So we'll set u to be the part that you'd rather differentiate, and dv is the part that you'd rather integrate, including the differential. Consequently, du is the derivative of secant, which is secant tangent, all times d theta, and v will be the integral of secant squared, which is tangent theta d theta. Let's encapsulate that into a box. We get 9 times uv minus integral v du. So we'll have secant tangent minus the integral of v du. That's secant theta tan squared theta d theta in square bracket. Now, we need to replace tangent squared theta with something involving secant squared theta, according to the identity we wrote down a moment ago. That's secant theta times secant squared theta minus 1 d theta. We'll distribute this secant to both terms and also distribute the minus. We have then 9 times the integral secant theta tan theta. We'll get a minus minus is plus the integral of secant theta d theta, and then minus the integral of secant cubed theta d theta. Now if you're paying attention, you realize that we still have the integral of secant cubed. So we started off with the integral of secant cubed theta. That ended up being secant theta tangent theta plus the integral of secant theta minus the integral of secant cubed theta. This is one of those cases where you need to move one term to the other side. If I bring a negative secant cubed to the other side, I'll end up with 2 of these. I'm trying to figure out the integral of secant cubed. All I have to do is multiply both sides by 1/2. So all of this gets multiplied by 1/2 after we drop this 2 over to here, bring this to the other side, and then divide by 2. That leaves us then with 9/2 secant theta tangent theta plus the integral of secant theta d theta. Do you remember the integral of secant theta? You might not remember, but the integral of secant theta is the natural log of the absolute value of secant theta plus tangent theta and then plus c. This was a garbage can calculation. Just to spark your memory, the way that we arrived at this was to multiply by 1. You can always multiply by 1 or add 0. This changes the form of the integral, but it doesn't change the value because we're multiplying by 1. When we distribute, we'll reverse the order of the sum to get secant theta tangent theta plus secant squared theta, and still divided by secant theta plus tangent theta. The derivative of secant is secant tangent. The derivative of tangent is secant squared. So this integral is in the form f prime over f, and those always end up with the log of f in absolute value. So this will be the log of the absolute value of secant theta plus tangent theta plus c. So our answer is 9/2 secant theta tangent theta plus the log of the absolute value of secant theta plus tangent theta plus c. At this point, we need to use a triangle to convert back to x. So with our triangle, tangent is opposite over adjacent, and the remaining side is obtained by the Pythagorean theorem to be the square root of 9 plus x squared. So we have 9/2. Secant is hypotenuse over adjacent. Tangent, x over 3, plus log absolute value, secant, plus tangent in absolute value, plus c. There's your answer. On problem 4, we have the square root of x squared minus 9. Now I'm running you through all 3 of the cases for a trig substitution in the practice exam. I won't give you all 3 on the actual exam just because we don't have time for you to do all 3, but you don't know which one I'll give you. So at least we have to run through an example from each of these cases. This is a secant substitution case because secant squared theta minus 1 is equal to tangent squared theta. So the square root of the variable is the square root of the constant times the function, in this case secant theta. So dx will be 3 secant theta tangent theta d theta. So we get the integral of square root 9 secant squared theta minus 9 times 3 secant theta tangent theta d theta. The 9 can come out as a 3 combined with the other one, gives us 9 times the integral. Secant squared minus 1 becomes tangent squared. Square root of that is tangent. We'll have secant theta tan squared theta d theta. And it's beginning to look a lot like the last problem here. Tangent squared is secant squared theta minus 1. So you'll have 9 times the integral of secant cubed theta d theta minus the integral of secant theta d theta. And if you remember from the last example, that's going to be 1/2 secant theta tan theta plus 1/2 the integral of secant theta d theta, and we still have minus the integral of secant theta d theta. Well, 1/2 of them minus one of them leaves you with minus 1/2 of them. So we'll get rid of the plus and replace that with a minus and get rid of the last integral. We'll have 9 times 1/2 secant theta tangent theta minus 1/2 log absolute value secant theta plus tangent theta plus c. It's at this point where we use the triangle again to make the substitution back to x. So the triangle uses secant theta, which is hypotenuse over adjacent. The Pythagorean theorem gives the remaining side to be the square root of x squared minus 9. So we have, I'll factor the 1/2 out. Secant theta, which we know to be x divided by 3, tangent theta, which is opposite over adjacent, minus log absolute value secant, which is x over 3, plus tangent, and then plus c. Running down the paradigm of integration methods, we've done substitution. We've done each case of a trigonometric substitution. Let's do partial fractions now. Let's see, I have x minus 1 squared times the irreducible quadratic x squared plus 1 dx. As you'll recall, this is an algebraic technique. We'll begin just by rewriting the fraction. And it's equal to a constant over x minus 1. Because the power here is 2, we have to include the possibility of a constant divided by x minus 1 squared. Power is 1 all the way up to whatever power appears here. For your irreducible quadratics, you need a linear term in the numerator, cx plus d, over the irreducible quadratic. If you now multiply both sides by the denominator, the left-hand side just becomes 1. On the right-hand side, we'll distribute that denominator to each of the 3 fractions. We'll have a times x minus 1 times x squared plus 1. One factor of x minus 1 will cancel. Plus b, in this case, both factors of x minus 1 cancel, leaving you with x squared plus 1, plus the quantity cx plus d, x squared plus 1 cancels, leaving you with x minus 1 squared. There are any number of ways of proceeding from here. One of the easiest things you can do is to let x be 1. If x is 1, then this term goes away, this term goes away. You end up with 1 equals 2b, and hence b is 1/2. The next obvious choice to choose for x is x equals 0. That doesn't drop anything, really. You'll have 1 times negative 1. You'll get negative a. You already know what b is. So if x is 0, you'll just have 1/2. If x is 0 here and 0 here, you'll just have plus d. So you end up with the equation negative a plus d equals, moving this over, 1/2. 1 minus a half is a half. That's one equation and two unknowns. You have one of the unknowns. There are four unknowns altogether. We need two more equations to nail this down. So let's choose other possible values of x and see if they do us any good as well. There are no real good choices for x, so we'll just play the hand that we've been dealt. 2 seems like a good choice because 2 minus 1 is 1. But you get 2 squared is 4 plus 1 is 5. That gives you 5a. You get 5b, that's 5 halves. And then you get 2 minus 1 is 1, squared is 1. You get 2c plus d. Let's see, if we move the 5 halves over, 2 halves minus 5 halves is negative 3 halves. We'll have 5a plus 2c plus d is minus 3 halves. There are no real good other choices. Let's choose x equals minus 1. Just for sake of argument, negative 1 squared is positive 1 plus 1 is 2. You'll have negative 1 minus 1 is negative 2, so you'll have negative 4a. And here you'll have 2b, which is 1. You'll have negative 1 minus 1 is negative 2 squared is 4. 4 times negative c plus d. That's negative 4c plus 4d. Moving the 1 over, you'll get the equation negative 4a minus 4c plus 4d equals 0. You may as well divide a 4 out in that case. So we can replace that equation by negative a minus c plus d equals 0. This gives us 3 equations in 3 unknowns. It seems one of the easiest things that we can do is combine these last 2 equations to figure out what c is. If I multiply this equation through by a negative 1, so a minus d is negative 1/2, I can add that to the other equation yielding negative c, and hence c is 1/2. Recall we already have b is 1/2. Now that we know what c is, we can plug that in over here and get the 2 equations. A minus d equals minus 1/2, and 5a, if c is 1/2, 2 times a half is 1. Move that to this other side, we'll have negative 5 halves. We'll have 5a plus d is negative 5 halves. Adding these 2 equations, 6a is negative 6 halves, and hence a is negative 1/2. So we have a is minus 1/2, b is 1/2, c is 1/2, and if a is minus 1/2, then d is 0 from this equation here. Now we can begin the integral. We'll have negative 1/2 over x minus 1 plus 1/2 over x minus 1 squared plus 1/2 x over x squared plus 1 dx. For sake of simplicity in the calculation, I'm going to move this up as x minus 1 to the negative 2. Also, I'll put this 1/2 out here. If we want to make this last term look like f prime over f, we're missing a factor of 2 here. The derivative of the denominator is 2x. I want 2x. I get what I want but I have to balance it out by putting another factor of 2 in the denominator. So we get negative 1/2 log absolute value of x minus 1. We'll use the power rule to write the next term as x minus 1 to the negative 1 divided by negative 1 plus 1/4 log absolute value of x squared plus 1 plus c. And we're essentially done. For purposes of the exam, put a box around it, you're done. In this case, the absolute values are superfluous, since x squared plus 1 is already non-negative. But out of force of habit, and it's a good habit, whenever you get a log, you should put it in absolute value for these sorts of integrals. We arrive at the last method of integration. So let's integrate x e to the 3x, and this clearly is an integration by parts problem. There's a portion of the integrand that you would rather differentiate than integrate. And so this is a clear integration by parts. U is the thing that you'd rather differentiate. dv is the thing that, well, it's everything else, including the differential. In this case, du is dx. V will be 1/3 e to the 3x. It's always uv minus integral v du. So x over 3 e to the 3x minus the integral of 1/3 e to the 3x dx. Our final answer is x over 3 e to the 3x. We'll get another 3 in the denominator, so it's going to be minus 1/9 e to the 3x plus c. I should mention that it's always possible to do these integrals by the tabular method. So x goes here, 1, and then you end when you get to 0. You have e to the 3x here. You differentiate down the first column, but you integrate down the second column. That's why we get a 1/3 and not a 3. And a 1/9. You multiply down diagonals and alternate signs. So you can see that we'll get x divided by 3 e to the 3x minus 1/9 e to the 3x plus c. Piece of cake. So in problem 7, it's the integral of x cubed e to the 3x. And this is obviously an integration by parts problem, but it involves 3 integration by parts. So if you're smart, you'll learn the tabular method because you can do them all in one fell swoop. So we'll have u and dv, x cubed, 3x squared, 6x, 6, and then 0. That's where you stop. E to the 3x, we integrate, so it's 1/3 e to the 3x, 1/9 e to the 3x, 1/27 e to the 3x, and 1/81 e to the 3x. Multiply down diagonals and alternate signs. Plus, minus, plus, minus. So you have x cubed over 3 e to the 3x minus 3 divided by 9, that's 1/3, x squared over 3 e to the 3x. 6/27, that's 2/9, plus 2/9 x e to the 3x, and then we'll subtract 6/81, that's 2/27 e to the 3x plus c. On problem 8, we're looking at the integral from 0 to 1, e to the t squared dt, and we're not evaluating this because, after all, e to the t squared has no elementary antiderivative, making the fundamental theorem of calculus impossible to apply here. So what I'm asking you is to estimate using Simpson's method with n equals 4. You recall that for Simpson's rule, the integral from a to b of your function is approximately equal to delta x over 3 times f of x naught plus 4 f of x1 plus 2 f of x2. You alternate 4 and 2 from here until you get 4 f of x and minus 1, and then a coefficient of 1 on the last term. So for us, delta x is going to be 1 minus 0 divided by 4. And the partition points will be 0, x1 will be a fourth, x2 will be a half, x3 is 3/4, and x4 is 1, so that we're dividing our interval 0 to 1 into 4 pieces, like this. So for us, delta x is 1/4. We divide that by 3, so the integral will be about 1/12. The function evaluated at the left-hand endpoint, that's e to the 0, plus 4 times e to the power of 1/4 squared plus twice e to the 1/2 squared plus 4 times e to the 3/4 squared plus e to the 1 squared, which is 1, e to the 1. And this is it. You'll drop the computation here for purposes of the exam. On problem 9, I'm asking you what value of n should you use to estimate this integral to 5 decimal places, so that your tolerance for error should be something smaller than 0.1234 5, and then no more than a 5. It'll be less than a 5 in the 6th decimal place off, so that you'll be accurate to the 5th decimal place. So that's 5 times 10 to the negative 6. That's your tolerance for error. The error formula for Simpson's rule is your delta x divided by 180 times b minus a times the maximum for x values within AB of the absolute value of the 4th derivative of the function. Well, for us, the function is cosine x, and its 4th derivative is itself. Delta x will be 1 minus 0 over n. The whole point is to figure out what n is. And so b minus a will be 1. We will have 1 over n times this 1, and the maximum for x values between 0 and 1 of the absolute value of the cosine of x. Well, cosine is no bigger than 1. So we'll bound this by something no bigger than 1. We'll have 1 over 180n. That must be strictly smaller than our tolerance for error, which is 5 times 10 to the negative 6. Rearranging this, you can see then that we'll have 1 over 180 times 5 times 10 to the negative 6 must be smaller than n. So n will be at least this value. And this is where you drop the computation, since I don't allow calculators on the exam. On number 10, We're integrating from 0 to 1, 1 over the square root of x dx. You'll see that the integrand is discontinuous at 0. So this is an improper integral. What is an improper integral? I guess you could say it's one that does inappropriate things in social settings, perhaps. No, anytime you integrate across a discontinuity, or one of the limits of integration is plus or minus infinity, the integral is said to be improper, in which case we have to set this up as a limit. As the lower limit goes to 0 from the right. We have to go to 0 from the right, integrate from L to 1. I'm going to rewrite the integrand as x to the negative 1/2 so that I can use the power rule. That gives us the limit as L goes to 0 from the right. We add 1 to the exponent and divide by the new exponent, and we're evaluating from L to 1. We have then the limit as L goes to 0 from the right of twice the square root of 1 is 1 minus 2 root L. Since L is going to 0 from the right, the limit will be 2. On number 11, we're integrating from 0 to 1, 1 over x minus 1. Again, this is an improper integral because we have a discontinuity at 1. So we have to write this as the limit as L goes to 1 from the left, going up to the 1 here, integral from 0 to L, 1 over x minus 1 dx. So that's the limit as L goes to 1 from the left, log absolute value of x minus 1, evaluated from 0 to L. That's the limit as L goes to 1 from the left, the natural log of absolute value L minus 1 minus the natural log of 0 minus 1. The natural log of 1 is 0, so this last term contributes nothing to the answer. But on the first term, L is going to 1 from the left, and so L minus 1 is going to 0. In absolute value, the argument of the log function will go to 0 from the right, and that's minus infinity. So we say that this integral diverges, but we can say better than that it diverges. It diverges to minus infinity. On problem 12, we're integrating from 1 to infinity of 1 over x squared dx. This is an improper integral because one of the limits of integration is infinity. The function's continuous between 1 and infinity, but one of the limits of integration is infinity. So we must express this as a limit as L goes to infinity, integral from 1 to L, 1 over x squared dx. That is equal to the limit as L goes to infinity. The integral of 1 over x squared is negative 1 over x. And so we have the limit as L goes to infinity of negative 1 over L minus negative 1 over 1. As L goes to infinity, negative 1 over L goes to 0. And so the answer is 1. There are certain things you just need to know. So these are like free points. The integral of sine of 7x dx. Well, the integral of sine is negative cosine, but we have a seventh. So we'll have negative 1/7 cosine 7x plus c. On problem 14 on the practice, we're integrating from 0 to pi sine x dx. I expect you to know that if this is 2 pi, this is pi, we're integrating one bump of the sine curve. And one bump gives you 2, half a bump gives you 1. You can verify this on your own using the second fundamental theorem of calculus. On problem 15, you should know that if you integrate cosine over half a period, you got nothing. On number 16, we're integrating from -1 to 1 x times the square root of x squared plus 1 dx. Now, a trained eye will recognize immediately that the integrand is an odd function, and whenever you integrate an odd function from -a to a, you get 0. This is as much work as I expect you to do on the exam, but you have to know that you're dealing with an odd function. So let's review that concept. What does it mean for a function to be odd? It does inappropriate things in social settings? No. It means f of negative x equals negative f of x. It's kind of like, as your prototypical example, f of x equals x cubed. F of negative x will be the quantity negative x cubed. 3 negatives is still negative, and so you get the negative of the original function. An example of a function that's even would be f of x equals x squared. Notice the even exponent. In which case f of negative x will be negative x quantity squared. The square gets rid of the negative, and so you end up with the original function. So a function is even if f of negative x equals f of x. So you may be wondering, why is this integrand odd? The integrand is odd because if f of x is x square root of x squared plus 1, then f of negative x is negative x square root of negative x squared plus 1. This negative can just be put out front. This negative gets squared away. And that leaves you with the negative of the original function. Therefore, it is odd. If f of x equals, if f of negative x equals negative f of x, whatever happens at x, you get the opposite at negative x. And whenever you integrate such a function over a symmetric region from -a to a, you have to get areas that cancel each other out. And so you have to get 0. Once you get the hang of it, you can recognize immediately that this function will have a negative that disappears here, one negative that preserves here. It's an odd function, and therefore, since you're integrating from -a to a, you have to get 0. On 17, I ask you to integrate from -1 to 1 the square root of 1 minus x squared dx. You might be thinking trig sub, but it's far easier than that. The curve y equals 1 minus x squared satisfies y squared equals 1 minus x squared, and hence x squared plus y squared equals 1, which you will recognize as the equation for a circle of radius 1. Since we have the principal square root, we only get the top half of the circle from -1 to 1. So we get half of the circle, the area of the circle of radius 1. You find the area of a circle by taking pi r squared, and so our answer is pi over 2. On problem 18, we're solving a simple differential equation. dy dx is 1 plus y squared over x. We can separate the variables by dividing the 1 plus y squared over and multiplying the dx over, and then integrating. On the left-hand side, you get the arctangent of y And on the right-hand side, ln absolute value of x. You'll note that I only included one of the constants of integration, since an arbitrary constant plus an arbitrary constant is still an arbitrary constant. I can move one constant to the other side and combine it with the other one. What is more, I'm not going to solve for y, I'm going to leave it, and I expect you to do the same. On number 19, we have y e to the y dy dx is equal to 2x over 1 plus x squared. In this case, you can separate the variables just by moving the dx over and then integrating. On the right-hand side, we have something that looks like f prime over f. If it were a 1 in the numerator, we'd have an arctangent of x. But because we have an x in the numerator, the derivative of x squared is 2x, it's going to be a log. On the right-hand side. On the left-hand side, we need to use integration by parts. We'll do the tabular method. Y is the thing we want to differentiate, and e to the y we will integrate. The derivative of y is 1, the derivative of that is 0. The integral of e to the y is e to the y. Integral of e to the y is e to the y. Multiply down diagonals and alternate signs. We'll have y e to the y minus e to the y. I won't write plus c because I can combine it with the other c on the other side of the equation. And that's that. And now for problem 20. We're using Euler's method. And oi, that's Euler, not Euler, it's Euler. Euler's method to approximate the solution to the differential equation y prime is the square root of 1 over y minus 1. And here we're assuming that y of 0 is 1/2, and that h, the increment that we're using, is 1/10. Now, Euler's method for differential equations like this would be yn plus 1 equals yn plus h times the function on the right-hand side evaluated at xn, yn. In this case, there are no x's over here, just y's. So we'll plug in our yn. We'll start by asserting that y0 is the initial data value. y1 will then be y0 plus 1/10 times the square root of 1 over 1/2 minus 1. And so simplifying this, 2 minus 1 is 1. We'll have 1/2 plus 1/10. This is 5/10 plus 1/10 is 6/10, or 3/5. So that's one of our answers. I want 2 iterations of Euler's method. So y2 will be 3/5 plus 1/10 square root 5/3 minus 1, and I'll permit you to drop the computation at this point here. And that's the exam review. I should mention that the actual exam will be much shorter. I wanted to make sure to give you an example of all the possible problems that could be on the exam during the exam review. But definitely you'll have far fewer than 20 problems on the actual exam.